Welcome back to Pivotal Polymers, your favorite new show about polymers on the PVC, Polymers Vital Content. I'm your host, Monomer. Our latest investigation may just help your next electronic mishap. Have you ever dropped your smartphone and cracked the screen? 50% of people globally have experienced a cracked smartphone screen at least once. Some of you would replace the cracked screen, which is by no means a cheap option, but many simply toss out the damaged phone. Imagine how much waste is being generated for every person who does that. How can we reduce this electronic waste? We could stop using computers, but I don't think that's remotely possible. Rather, we can rethink the materials. One powerful way to do this is to make the electronics flexible. Traditional electronics are fabricated based on rigid and brittle components, such as silicon and glass. Take, for example, this glass slide. It's not flexible, stretchable, or bendable. If I try to bend it, it breaks. See? However, in the near future, we will not have to worry about damaging electronic devices from simply dropping or bending them by sitting on them. Flexible electronics has been an area of interest for the past few decades. Many areas of our everyday life will benefit from introducing these flexible electronics. Electronics will become easily wearable, rollable, and robust. The biggest key to achieving flexibility is using rubber-like flexible polymers. Several different polymers will be inside these devices, so the overall build of the flexible devices needs to meet several critical requirements. First, each component layer in the device should be thin enough to be easily deformed. Second, compact contact between different components should be made to avoid cracking and separation during deformation. Last but not least, the third requirement is that the component's mechanical and electrical properties should remain stable during deformation. Many polymer materials already meet these requirements. One example of this is a flexible battery. For a flexible battery, metal electrodes get smaller and thinner, down to 100 nanometers thick, and then they are wrapped by a flexible polyamide. The flexible battery functions well when stretched and also returns to its original shape. These are the general ideas of polymer flexible electronics, but we still need to ask, what does it mean to be a polymer flexible electronic? When and who invented them? What's the future of these things? Let's go to Felix A. Bell to find out more about their history.
Thanks, Mona. Until the 1960s, no one could imagine polymer flexible electronics. People didn't believe there were things like conducting polymers. However, in 1977, Alan Heger, Alan Madiramid, and Hideki Shirakawa changed this view with their discovery that a polymer can be conductive almost like metal. They found polyacetylene became conducting after it was oxidized with halogens. For this research, they were awarded the 2000 Nobel Prize in Chemistry. Since this surprising discovery, many research teams have worked on developing new conducting polymers and their applications in polymer flexible electronics. One of the many exciting applications are flexible displays, which use polymer light-emitting diodes or LEDs. And the first flexible polymer LED was also reported in Nature 2 years later. Many companies developed polymer LED prototypes in the early 2000s. Since late 2000s, flexible polymer LED have been released to the press. In 2007, Sony's research group introduced a flexible polymer LED display, and they upgraded their displays to be rollable in 2010. In the same year, a 4.5-inch high-resolution flexible polymer LED display was introduced by Samsung. After only 2 more years, the size of the display reached up to 112 inches. In 2013, the first paper-slim curved OLED TV was launched, and now it rolls.
Thank you, Felix. It's hard to believe that the quick acceleration of our discoveries related to these electronics, but what do our leading researchers think about the current state of the field? Maddie Serial is here to give us some insight.
Okay, so I think it's really critical to make a thin polymer like substrate to be used in the flexible electronic. But I'm also curious, what would be the advantage of the organic material over inorganic material in the flexible electronic?
Now, the real beauty of an organic polymer really does come down to molecular weight. The molecular weight is very high in a good polymer, and because of that, there's a lot of interactions between polymer chains. In fact, in kind of a model, you might imagine if you've ever taken spaghetti and you've cooked it, and then you let it sit and become cold, how all those spaghetti chains congeal together and you pick the whole thing up as one piece. It's very similar in the case of a solid polymer. And so what you could imagine is these chains will be wound around one another. They will have entanglements, that we might call it. They have the possibility of crystallizing, but when they crystallize, some of the chains will crystallize in one crystallite, and then they will move to another crystallite, and we will call those tie chains. And there are going to be amorphous regions, all in the same material. And so because of this semi-crystalline nature, then what we end up with is a material that can flex quite a bit without developing those cracks.
But might be still we have the challenge like to use polymer for the flexible electronics. So could you explain a little more about it?
Sure, absolutely. I think the thing you need to think about here is, what are the properties that you need to obtain? Metals have very high electrical conductivity. ITO has a high conductivity. And conducting polymers can have high conductivities, but even to this point, they are not as high as ITO or as metals, especially with the other properties that those materials bring. So indium tin oxide is optically transparent, while at the same time having this high conductivity. And so this is an area where we work. We recently published a paper using PDOT as an electrode material in electrochemical devices, where one of my postdocs, Michelle de Kiersmacher, developed compositions of PDOT with conductivities on the order of 2,000 to 3,000 Siemens per centimeter.
Okay, thank you so much for taking your time for the interview today, and then we learned a lot of the polymer flexible electronic today, and then hopefully we have time to visit your office again. And then
Welcome back. Polymer electronics are the hot topic today, and we left off with some fundamental discussion, but the real meat of the problem is how. Let's talk to a more informed person on the subject. Daria Oletti, over to you.
Having seen the key components of polymer flexible electronics, now you might wonder how they are put together as a functioning device. For most flexible electronic devices, you must have a flexible substrate, then the flexible electronic circuits on top. It's not necessarily difficult, so you might be able to make one at home someday. The fabrication methods can be divided into two categories. 1. Direct fabrication of circuits on flexible substrates. 2. Transferring circuits from rigid substrates to flexible substrates. Additive manufacturing, also known as 3D printing, is one of the most promising methods to fabricate flexible electronics. This is an aerosol jet printer. It's not really a 3D printer because it only prints thin layers for most of the time. The desired materials are dissolved in solutions and put into these atomizers to be vaporized. The vapor goes through the tube and comes out from the nozzle. In this way, a variety of materials can be directly printed onto desired substrates, including flexible or stretchable ones. Transferring electronic circuits from rigid substrates to flexible ones is another way to fabricate flexible electronic devices. First, the circuits are fabricated on rigid substrates such as silicon wafers. Patterning, masking, etching, which are the standard way you will fabricate conventional electronic circuits. Then stick the flexible silicon on the wafer and strip it. The circuit seems to like the flexible substrate more, so the actual fabrication process is much more complicated than this. A lot of physical and chemical treatments must be applied in order to fabricate a reliable device, but this is the basic idea. A stunning simple way to fabricate flexible electronic devices is developed recently. First, print a pattern on a sheet of tattoo paper with an ordinary laser printer. Then put silver epoxy that only sticks to the printed pattern. Apply a liquid alloy on top to enhance conductivity and flexibility. Attach electronic parts with conductive glue. The flexible electronic device can be transferred onto objects with the help of a bucket of water. Hopefully, this technique will be available to ordinary people in several years.
Thank you, Daria Oletti. Today, our computers, smartphones, and even cars all rely on engineering that has made electronic circuits smaller, faster, and smarter. Why do we want polymers, though? Let's join Sherlock Phones as he sits down with Professor Kaplan's lab to find out.
Okay, so thank you very much. Good afternoon, Professor Kaplan. Thank you very much for giving us this opportunity to have a talk with you about polymer flexible electronics. So why do you think flexibility is so important for electronics?
We want materials that mimic the mechanical properties of skin. So skin is soft, it's stretchable, and you can develop devices that have these different functions, but that are conformable. And so the ability of being able to attach something to an object of any shape, I think that's very powerful.
Okay. Someone can have to think about polymers in flexible electronics. What is the role of polymers into flexible electronic applications?
If you make a polymer, which is an assembly of a lot of blocks, and you can make very large macromolecules, these materials are soluble in a lot of different solvents. And so you can formulate inks, and these inks are liquids. And so these liquids, you can process them into thin films using various printing and coating techniques at room temperature, onto any substrate, and that's what makes polymers so attractive in terms of the technology. So the ability to be coated onto any substrate at low temperature.
That was Professor Kaplan and Sherlock Phones. No matter what the future of polymer flexible electronics will be, it will be fascinating to watch. Join us next time for more investigative reports on all things polymers. Thanks for tuning in to the PVC Network.